Right, our datasheet talks about the TRAPPIST-1 system, and all of those planets in the TRAPPIST-1 system are closer to their sun than Mercury is to our sun. This means that actually it's a very plottable graph, unlike the one in version 1. So, first off, we are asked to complete the table of values to 3 significant figures. So what we're looking at is we've got an R value, so we need to cube it. We've got the next R value, and we're going to need to cube that. The next R value needs cubing, and the next R value needs cubing. And the T, we have T squared, so these numbers are just squared. Okay, so plotting T squared against R cubed, if you look at our equation, it gives us a hint that this is going to be on our y-axis and this is going to be on our x-axis. So, plotting this graph, the easiest way to do it is going up in 50s along the bottom for your R cubed value and 20s up the side for our T squared values. What you'll hopefully notice is you end up with a pretty much dead straight line, and it goes through 0, 0. We know it goes through 0, 0 because we don't have a plus C on the end here for an intercept. So for part B, we need to draw a graph and do a line of best fit. By using your graph or otherwise find a value for K, if you look at this, you've got T squared, which is the equivalent of your Y. You've got R cubed, which is the equivalent of your X. We don't have a plus C, so that tells us it goes through the origin, and that K is going to be our gradient. Now, when we work out the gradient, the easiest way to do that is to pick 2 points that are as far away from each other as possible and still on our line. So, for part C, if we use the point 0, 0, because we know it goes through that, and we use the point 3, 4, 8. So as long as this point here is on our graph, is on our line, we can use that. So to find out what K is, we do change in Y over change in X. And that gives us an answer of 0.440 to 3 significant figures. Express T squared in terms of R, what this is telling us is we are only allowed to use these letters in our equation. Everything else has to be numbers. So for part D, we can write it as T squared equals our value of K times by R cubed. And that's it for that one, because you did all of the working out in the previous question. Okay, so part E. We know that the distance is this million kilometres. Now, what's important here is that R is also in million kilometres, so we don't have to deal with all of the zeros. What this tells us then is that R is 9.29. So if r is 9.29 and we want to find out t squared, we're going to have to work out what r cubed is. So r cubed is 1.8. So if we substitute that in, we've got an equation of t squared is 0.44 times 801.8. Then we're going to need to square root that to find out what t is. So t is going to be the square root of these two things times together. Okay, if you are square rooting something, you get a positive answer and a negative answer. However, we are only going to need to deal with the positive answer because we're looking at the length of an orbit, and that's not going to be able to be negative. So we are looking at 18.8 days. Okay, so part F, we are told the orbit is 2.42. So we know what t equals, and we need to find the distance from the sun. So if we grab a blank bit of paper, that'll do. Okay, so we know for part F, we know that its orbit is 2.42 days, so we can square that, and that comes in at 5.8564. So we know that 5.8564 is equal to our value of k, r cubed. So from here we just need to do a little bit of rearranging. So if we divide this side by this, we end up with r cubed is 5.8 divided by 0.44, and then we're going to need to cube root that. So we want the cube root of 13.31, so r is equal to 2.37, and that is being measured in million kilometres.